In addition to geometric series, telescoping series are also fairly easy to sum. In example 7, we will evaluate the series by finding the limit of the sequence of partial sums. Before we begin example A, please correct the lower limit of summation to be n equals 1 so that our first term will be defined. With that correction, we can begin generating our sequence of partial sums. Recall that the first partial sum is simply the first term of the sequence. Plugging in n equals 1, we have the value 1 minus 1 over 1 plus 1, or 1/2. Of course, the sum here is 1/2, but I'm not actually going to execute these sums in order to demonstrate the pattern of the telescoping series. So let's go ahead and move on to the second partial sum. The second partial sum is the first term plus the second term. Now for the second term, I'm using this formula and plugging in n equals 2. We have 1/2 minus 1 over 2 plus 1, or 1/3. Observe that the negative 1/2 and the 1/2 would cancel, and this partial sum would telescope down to the very first and last term. You're going to see this behavior on the third partial sum as well. Recall, the third partial sum is the sum of the first 3 terms of the series. So plugging in n equals 3, our last term would be 1/3 minus 1/4. Once again, we see the sum telescoping down to the very first and the very last term. We can assume that this pattern continues until we get to our nth term, or our general term for the partial sum. So we know this cancellation pattern is going to continue. All the way to our nth term. So just as these interior values are canceling, we can assume that 1 over n will cancel with the term just prior to it. Therefore, the formula for the nth partial sum of this telescoping series is 1 minus 1 over n plus 1. Recall that the sum of the series from n equals 1 to infinity of 1 over n minus 1 over n plus 1 is the limit of the sequence of partial sums. We have the nth term formula for that sequence of partial sums. So to evaluate the sum of the series, we just need to evaluate this limit. Clearly, this limit is equal to 1. Therefore, the sum of this series is 1. So unlike the geometric series, where we apply a specific formula to evaluate the series, here we are back to using the nth term formula for the sequence of partial sums, calculating that limit to determine the value of the series. Let's look at another example that is a telescoping series in disguise. To find the sum of this infinite series, we're first going to do some algebraic work on this formula right here. So I'm going to take this out and split it up into separate fractions using our technique of partial fractions. So we've got 2 distinct linear factors in the denominator. So we're going to create 2 partial fractions, each with a constant numerator. Recall that the next step in partial fractions is to multiply both sides by the lowest common denominator that we have on both sides. See if I can slide it in over here. So on the left side, the denominators of course cancel, leaving behind a 1. If we distribute to our first term here, the 3k plus 1 will cancel, and we'll be left with 3k plus 4. And distributing here, the 3k plus 4 cancels, and we have 3k plus 1 left over. At this point, you have the choice to either write the right side as a polynomial in k in descending order, or because this is an identity, you can choose convenient k values to zero out one factor at a time and find a and b. I'm going to go for the latter method. So I'm going to use k equals -4/3. Plugging in k equals -4/3, the first term cancels out or zeroes out. And for the second factor, we end up with b times -3. So we can see that b is -1/3. Another convenient k value to use would be the 0 of this other factor, -1/3. Plugging in -1/3 on the left, we have 1. Plugging it on the right side, we have a times 3, and this factor zeroes out. So it looks like a is equal to 1/3. Thus, we can take our original series and rewrite it using our new model. We have the sum from k equals 0 to infinity of a, which is 1/3, over 3k plus 1, plus b, and we discovered that to be -1/3, over 3k plus 4. Now, this summation is an operator, and like many of our operators, such as the differential operator, the integral operator, we can factor corresponding or common coefficients in front of that summation. So I'm going to factor out the 1/3. This is going to leave behind 1 over 3k plus 1 minus 1 over 3k plus 4, and this will turn out to be a telescoping series. To find the sum of this telescoping series, we're going to find the sequence of partial sums. Now, I'm going to temporarily ignore this 1/3. We'll come back and pick it up at the end. And by the way, we're going to start with our 0th partial sum because our summation starts at 0. So plugging in k equals 0, we have 1 minus 1/4. Again, I'm not going to simplify that because I want to examine the pattern that's generated. Plugging in k equals 1, for our second term, we have 1 over 4 minus 1 over 7. So to be clear here, this is our first term. This is the sum of our first term a0 and the next one a sub 1, and observe those 1/4 cancel and the sum telescopes down to the first and the last value. Let's go ahead and generate another partial sum. Let's do 2 next. How many of these terms do you need? Only as many until you feel confident with what the actual pattern is. Now, we're going to plug in k equals 2. We're going to end up with 1/7 over 1/10. And like we have seen with the previous partial sums, this will telescope down or condense to the first and the last value. Continuing this pattern, we can say then the nth partial sum will have similar behavior. That is, it will telescope down to the very first and very last terms. So we're going to end up with 1 over 3n plus 1 minus 1 over 3n plus 4, where everything in the middle cancels, including this term, which would cancel with the 1 just prior to it. Thus, the nth term or explicit formula for our sequence of partial sums is 1 minus 1 over 3n plus 4. Our conclusion then is that the sum from k equals 0 to infinity, this is our original series, is equal to the limit of the sequence of partial sums. We now have an explicit formula for the sequence of partial sums, and again, this limit turns out to be 1. So the infinite sum of this telescoping series is 1. Telescoping series, once again, are pretty easy to handle. Even though they don't have a formula like geometric series, these patterns that we can generate are pretty easy to recognize. And don't forget about the tool of partial fractions if you happen to run into one that looks something like this.